Welcome to Module 2. In this module, we will discuss multivariable function, especially function of two variable and its properties. In this session, we will see what is a function of two variable, and also we will discuss the concept limit and continuity of such functions. Okay, before introducing function of x and y, I would like to analyze function of one variable. So we consider y is equal to f of x. It's clear that here f is a function of single variable. And also we know that here this x is independent variable and y is dependent variable. Then what is the meaning of this representation? This means for a specific value of x, this function assigns a unique value. That means the specific values of x, y has a unique value. The dependent variable y has a unique value. Similar concept, we can extend the similar concept to functions of two or more variables. Okay, so how to extend this concept? You consider z is equal to f of xy. Then what are the independent variables? As similar to single variable function, it is clear that here x and y are the independent variable and this z is dependent. And what is the meaning? The specific values of x and y that gives a unique value for z. This function assigns a unique value for z. Okay, so this is the concept of two variable function. Similarly, we can extend this concept to any number of variables. Okay, anyway, this is the formal definition of two variable function. A function f of two variables x and y is a rule that assigns a unique number fxy. So this fxy is the unique number to each point xy in some domain some set D in xy plane. Okay, because x and y moving in xy plane. Clear? So this is the meaning of function of two variable. Similarly, we can extend this concept to three variable case. This f of x, y, z. Only thing is here x, y and z all are independent. That will be w. W equal to fx, y, z. That means w is dependent and this x, y, z are independent variable. Okay. So this is the idea of multivariable function. So they are called multivariable function. Multivariable means a function involving two or more variables. That's all. So consider this example that fxy is equal to square root of y plus 1 plus log of x square minus y. This is a two variable function. This expression involves two variables x and y. Here x and y are independent. You can choose any value for x and y. Okay, such that this expression is valid. That is very important. We have to find f of e comma 0. Okay, how to find f of e0? We have to substitute x by e and y by 0. So here this becomes square root of 0 plus 1. This is log of what about x square? E square minus 0. So this is log e square. Okay, so this expression become, okay, this is square root of 1. What is square root of 1? That is 1. Here, okay, the square root of 1 means it is a positive square root. Okay, that is a globally accepted notation. Square root means positive square root. So this become 1. And what about log e square? This is a natural logarithm, base is e. So log e square is 2. Yes. So this become 1 plus 2. That is equal to 3. So this is the unique value corresponding to the choice of this particular choice of x and y. If we choose x as e and y as 0, then this f gives a unique value, that is 3. Okay, that's the idea of two variable function. Similarly, we can extend this concept to n number of variables. Okay. Yes, answer is 3. Okay, sketch the graph of this function z is equal to square root of 1 minus x square minus y square. That means we know that how to sketch a single variable function y is equal to f of x. We take x in this direction, y is in this direction, then you assume that x has this particular value, then we find what is the corresponding value of y, then we mark this point. Continuing in this manner, you get the entire curve. Similarly, how to plot z is equal to fxy? That's our question. Okay, z is equal to a function of xy. It is clear that here xy moving along a plane. Okay, it is clear that suppose this is our x-axis and this is our y-axis, then xy is moving along this plane. So corresponding to each xy, there is a unique value. There is a unique value for this function that is on the z axis. Okay, so suppose xy is here, then its corresponding z value is there. So maybe suppose x is 1, y is 2, then z value is suppose 7. Then 1, 2, 7 gives a single point in 3-dimensional space. Okay, similarly you can plot all such 3D points. So it form a surface in 3D. Okay, so z is equal to fxy gives a surface in 3D. Okay, y is equal to fx gives a curve in 2D. Similarly, z is equal to fx give a surface in 3D. Okay, then how to plot such functions? Okay, then this is a very simple function. You can easily plot this. What is this? It is clear that z is equal to positive square root of 1 minus x square minus y square. So the one direct implication is z is always non-negative because this is a positive square root of. So the minimum value of z is 0. Then how to plot this one? Or what is the relation between x, y, z? If you square this expression, this gives z square is equal to 1 minus x square minus y square. If you take this x square and y square on this left side, this becomes x square plus y square plus z square equal to 1. And what is this? This is a very familiar surface. Yes, it's a sphere, equation of sphere with the center origin and radius is 1 because it's 1 square. So radius is 1. But we know that the sphere is like this. Okay, but our equation is actually z is equal to positive square root of 1 minus x square minus y square. So z should be positive. So it is clear that this surface is a part of this sphere. This surface is a part of sphere, but there is a restriction. Z should be positive. So which part of the sphere? Yes, upper part of the sphere, the upper hemisphere. Clear? So that is this surface. If you sketch the surface, then you get like this. The upper hemisphere of x square plus y square plus z square equal to 1. Clear? Next problem, sketch the graph z is equal to x square plus y square. Okay, here our fxy is nothing. Fxy is x square plus y square. Clear? So how to plot this function? And this also gives one important thing, that is z is non-negative because z is equal to x square plus y square. So whatever be the value of x and y, z is always positive. So this is x-axis, this is y-axis, or z-axis. Then the guarantee is surface is on the upper side of this plane xy, upper side of this xy plane. This is our x-axis, this is y. We assume that this is our z-axis. Okay, that is guarantee. Then how to plot it? So suppose our z value equal to 0. Then what about x and y? If z equal to 0, this equation gives 0 equal to x square plus y square. This implies what? What is the value of x and y? Both are equal to 0. So 0, 0, 0. So this point. Clear? Next you assume that z equal to 1. We simply assume some different values of z for understanding the shape of this surface. Okay. When z equal to 1, what happened? This expression become 1 equal to x square plus y square. And what is x square plus y square equal to 1? Yeah, of course, it's also a circle with the radius 1. And what is the position of this circle on the surface, on this this 3D surface? Actually, surface is actually x square plus y square. Suppose this is our x square plus y square. But its z value is always 1. So this circle is not here. Its position is like this, somewhere here. This height is 1 unit. Clear? So if we choose another value of z is equal to 4, then what happened? Then this equation becomes 4 equal to x square plus y square. Again, it is a circle with the center origin and radius 2. So what is the value of z? Z is 4. So the position of the circle is at somewhere here. Suppose this is our 4. Then its radius is 2. So continuing in this manner, we have so many circles. Some is a smaller circle, smaller than this one and bigger than this one. And you get so many circles. So you think about the totality of these all circles. You think this contains infinitely many circles in the size increasing order, increasing size. Then what about this whole surface? Because the whole surface is getting by adding all such circles. The totality of this all circles is almost like this. Either it is a cone shape or it's a paraboloid shape. Is it cone or paraboloid? To identify it is cone or paraboloid, we have to take the cross section, vertical cross section. Okay. Suppose we consider a cross section in this direction. Okay. That means we are going to find the intersection of xz plane and the surface. That gives a cross section like this. And what is the intersection of xz plane and this surface? To find the intersection, what is the value of z on this plane? On xz plane, y value equal to 0, right? On xz plane, y value equal to 0. So you simply substitute y equal to 0. So this gives z is equal to x square. So this is the cross section on the plane, on the xz plane. So what about this one? Is it a parabola? Because we know that parabola in xy plane is y square equal to x or x like that. Y square equal to 4ax or x square equal to 4ay. Both are the representation of parabola in xy plane. So this is almost like that. Z is equal to x square. Only difference is this is on the zx plane, xz plane. Okay. So this cross section is parabola. So its shape is like this. So this is called paraboloid. Okay. Yes, this is the shape. So in general, z is equal to f of xy represents a 3D surface, a surface in 3D. Okay. Okay, next we are going to define the concept of limit in two variable function. Before introducing this concept, first we have to analyze what is the concept of limit in one variable function. Okay, in the case of one variable function, let it be y is equal to f of x, and we know this is the notation of limit extending to x naught, f of x equal to L. And what is the meaning of this representation? This means whenever x tends to x naught, that means x is very close to x naught, this f of x is very close to L. That's the meaning. Okay, geometrically, whenever x is close to x naught, then f of x is close to this L value. Clear? And in the case of one variable function, there is only two directions. Either x can tends to x naught through left side, or x can tends to x naught through right side. Okay, that's why we define two limits, left hand limit and right hand limit. Also, we know that under what condition limit exists. If left hand limit is equal to right hand limit, then we say that limit exists, and it should be finite. Okay. Anyway, left hand limit is equal to right hand limit, then we say that limit exists in the case of one variable function. What is the difficulty in two variable function? In the case of two variable function, here our x axis, this is y axis, and suppose the point x naught y naught. Suppose xy tending to x naught y naught. What is the complication? The complication is here xy, suppose you consider xy. Here xy can tends to x naught y naught in any direction. There are infinitely many directions to converge xy to x naught y naught. Okay. So the concept of limit in two variable function or many variable function is very complicated than this single variable function, because in this single variable function x can tends to x naught either left or right, so we have to bother about only two limits. But here xy tends to x naught y naught in any direction, infinitely many directions. Okay, that's a difficulty in two variable limit, the concept of limit in two variable function. Then how to define the limit? The concept is almost same as single variable function. Okay, so this means whenever xy is very close to x naught y naught, then f of xy is close to L. Again, denote this is like this: limit xy tends to x naught y naught, f of xy equal to L. So this means whenever xy is close to this point x0 y0, whatever be the direction, this fxy is close to this number L. Okay, that's the idea. Okay, these are the other representation of this concept. You can write like this: x tending to x0 and y tending to y0, f of xy equal to L. Or you can write this one: f of xy tending to capital L as xy tending to x0 y0. This means whenever xy is close to x0 y0, this f of xy is close to L. Okay, it doesn't mean that f of xy equal to capital L, only tending to L. Okay, so these are the different notations of the concept limit in two variable function. Consider this problem. Find limit xy tending to x0 y0, xy tending to 0 0 minus xy by x square plus y square. This is our function of xy, and we have to consider two different paths. First of all, we have to find this limit along the path x equal to 0. Also, we have to find this limit along this path. Okay, because this is a two variable function, so we have infinitely many directions such that xy can tend to 0 0. Okay, in the case of one variable function, we have only two directions. Here we have infinitely many directions. In this problem, we have to find the limit along these two directions. Okay, then what is x equal to 0? X equal to 0 means what? X equal to 0 means y axis. In this y axis, x value is always 0. That means our xy tending to y axis, either this direction or this direction. Okay, so it is clear that when x equal to 0, whatever be the point may be 0 1, point may be 0 0.5, like that. Okay, these points are tending to 0 0. So whatever be the point, is x value is always 0. So what about this numerator? The numerator is 0 because x is always 0. Divided by this x is 0 by y square. And what is the limiting value? Now x is always 0, only thing is y tending to 0. So 0 by y square, whatever be the y value, y is only tending to 0, y is never 0. So this expression becomes 0. So along x axis, its limiting value is 0. You got it? So next we consider another path. Another path means along the path y is equal to x. And what is y is equal to x? Y is equal to x means we know is a straight line like this. So xy tending to this path means either xy tending to this direction or xy tending to 0 0 through this direction. Whatever the points are always satisfying this condition. Okay, so what is the limiting value along this path? Okay, it is clear that over this path x and y are same, so you can replace this y by x. So this expression become minus x square by x square plus x square, right? X square plus x square over this path. So this is again limit xy tending to 0 0. Denominator is 2x square. You can cancel this x square and this become minus 1 by 2. So there is no part of x and y. So whatever be the value of xy, this is always constant. So its limiting value is minus 1 by 2. Clear? So the thing is, if xy is tending to along these two directions, its limiting value is 0. If xy is tending to 0 0 along this direction, then its limiting value is minus 1 by 2. So what is the conclusion? This limit exists or not? This limit exists or not? The limit doesn't exist, because limit exists only when this limiting value is always same. Whatever be the direction, its limiting value should be same. But here limiting value is different in different paths. So this limit doesn't exist, but along this path its limiting value is 0. Along this path its limiting value minus 1 by 2. Okay, this is the concept of limit. Okay, 0 minus 1 by 2, and this limit doesn't exist. Clear? Okay, now we are ready to define the concept of continuity in two variable function. Before that, we have to just analyze the concept of continuity in one variable function. Okay, we consider a function y is equal to f of x, and suppose this is the graph of this function, and it is clear that this function is continuous at x naught. Then what is the mathematical definition of this concept, continuity? Geometrically, continuity means there is no break. That is the concept of continuity. Then what is the mathematical definition of this continuity? Yes. Limit x tending to x naught, f of x is equal to f of x naught. Yes, this is the condition of continuity in one variable function. So that means whenever x tending to x naught, this f of x tends to some value, that value should be equal to f of x naught. Then only we can say that this function is continuous. Geometrically, there is no break. Okay. Similarly, we can extend this concept in the case of two variable function. So what is the definition? What do you expect? Yes. Analogous to this, we can define the concept of continuity in two variable. Limit x comma y tending to x naught y naught, some point x naught y naught, f of xy is equal to f of x naught y naught. Okay, so this is the definition of continuity in two variable function. Limit xy tending to x naught y naught, f of xy is equal to f of x naught y naught. Okay, this is the mathematical definition of continuity. Geometrically, what this means? Geometrically, this means there is no break at this point. We know that fxy, z is equal to fxy is a surface. That means there is no gap in that surface at this point. So geometrically, fxy is continuous if the surface means z is equal to fxy, that represents the surface. That surface has no tears or holes. Clear? Okay, consider this problem. Find the limit xy tending to 0, 0, 1 by x square plus y square. Okay, so we have to find that limiter. What is the meaning? What is the meaning of this cell, or what is the property of this cell? Whenever xy tending to 0, 0, whatever be the direction, this 1 by x square plus y square tending to somewhere, some number. Okay, that's the concept. Suppose xy tending to 0, 0. Then what about the denominator x square plus y square? Xy tending to 0, 0 means x and y both are tending to 0. Both are tending to 0 means this squared sum tending to 0. Clear? Because x and y both are tending to 0. So x square plus y square also tending to 0. And one more thing is, what is the sign of this tending number, this x square plus y square? Yes, it is always positive because it is x square plus y square. So this is a positive thing and tending to 0. That means very, very small positive quantity. So what about 1 by? So what about 1 by this quantity, x square plus y square? This is a very small positive quantity. So 1 by this is very big. That means this is tending to infinity. Clear? So whatever be the direction of xy, if x and y are very small, then x square plus y square is also very small and positive, and 1 by that is very big, very high, that is tending to infinity. Okay, so what is the limiting value? So its limiting value is nothing, its limiting value is infinity. So limit tending to infinity. So naturally there is a question. Is it continuous function? Is it continuous at 0, 0? Is it continuous? No, because its limit exists. Limiting value exists and limiting value equal to infinity. If it is continuous, then what is the condition for continuity? If this limiting value equal to f of x naught y naught, here x naught y naught is 0, 0, f of 0, 0, then only it is continuous. But what about this f of 0, 0? F of 0, 0 means 1 by 0 square plus 0 square, right? This is our f of 0, 0. This is equal to 1 by 0. What about 1 by 0? It is doesn't exist. Okay, 1 by 0 is doesn't exist. So here limit is infinite. The f of 0, 0 doesn't exist. So you can't equate it. Okay, so here limit exists, limit equal to infinite, but it is not equal to f of 0, 0. So it is not continuous at 0, 0. Okay, so here limit is infinite. Actually, infinity is not a number. It means it means very, very big. That's all. Infinity is not a number, not continuous at 0, 0. Actually, this is the graph of this shape of this surface. It is almost like this. Whenever xy tending to 0, 0, its function value is going to very large. Okay, but anyway, there is a gap at 0, 0 because this function is not defined at 0, 0. Clear? Okay, consider this surface. Already we know that it's a upper hemisphere of a sphere, upper hemisphere of radius 1 and center origin. And what about this surface? Is it continuous? Yes, we know its surface is like this. There is no tears or holes in the surface, so it is clear that this is a continuous surface. Clear? Similarly, this represents this inverted cone, and this also continuous. There is no break in this surface. Okay, so this also represents a continuous surface. Also, there are some standard results for continuous functions as similar to one variable function. Polynomial expressions and exponential functions in 2 or 3 variables, they are all continuous. For example, this is a polynomial expression in 2 variable function. This is an exponential function in 2 variable, all are continuous as similar to one variable function. And next one is composition of continuous functions is again continuous. Here we can define two functions like this f of u equal to sin u, and sorry, you can take this g of u, and some h of xy is equal to 5 x square y. Then you can write this f as g of h of xy, right? G of hy. If you apply the function g on this h, this gives sine of 5 x square y. So this is composition of functions. So sin u is continuous, this also continuous, so their composition also continuous. This is also similar to our one variable function. Another analogous results in two variable function is sum, difference, product, all are continuous. If you consider two continuous functions, then their sum is also continuous. And last one is quotient of continuous functions is also continuous. Only exception is denominator is non-zero. Okay, if denominator is non-zero, then the quotient is also continuous. So these are the standard type of continuous functions similar to our one variable function. Okay, so that's about this session. So I think all of you understood what is a function of two variable or three variable function, multivariable function, and also the concept of limit and continuity in two variable function. Okay. So in next session, we will define the differentiability and partial derivative, the concept of partial derivative of two variable functions. Okay. Thank you.